Good morning. So did everybody have a good break? Happy to be back. 8:30 chemistry class. Can't beat that.
Did you have a good break?
Yeah, I did. It, no offense, but it was nice not to be here. So. I'm expecting 3 more beings, so. Okay, we'll go ahead and get started. We'll go ahead and get started. So the first week, I need to take attendance because if you don't show up to the classes first week, they drop you from the class. So, I'm going to go ahead and call a roll, and please answer here for me. And just so everyone's clear, this is second semester of Gen Chem. So if you think it's something else, you're in the wrong room. Carolyn Ahi.
Here.
Bailey Barber. Matthew Cathro. Scott Detweiler.
Here.
Evan Ellis.
Here.
Taylor Friend.
Here.
Alex Hoke. Here. Jalen Holdaway.
Here.
Taylor Kearney. Taylor Kearney. Bethany Lancaster.
Here.
Marissa Lanzati.
Here.
Blake Miles.
Here.
Jalala Muhammad.
Here.
Erna Pilipovic.
Here.
Conrad Powell. Jacob Schaffer.
Here.
Jacob Schulstens.
Here.
AJ Siebert. Here. Okay. And then Marco. All right. And then Mia Maddock.
Here.
Okay, did Taylor Kearney? Kaylin Kearney?
Kaylin.
Okay, sorry about that. All right, so we have everyone, great. So what we'll do today is we'll kind of go over the syllabus because there are a few things I just want to highlight based on some of the questions that came up last semester. And then we'll start on chapter 11. Unfortunately, before we start, I do have some sad news to share with you. You may have heard this, but Professor Namani, who some of you may have had for lab, passed away December 17th. And so for those of you who, when you signed up, thought you were getting Professor Namani for lab this semester, obviously that's not going to happen. And so they've had to do some shifting around to cover for him. So anyway, if you knew Professor Namani, that's sad news. If you didn't know him, it's still sad news, but maybe not quite as impactful. So. All right, so just to remind everyone who took the class last semester, and I know we have some new people this semester, so everything gets posted on Canvas. So this syllabus is on Canvas. The lectures are posted on Canvas. Once again, similar to last semester, we'll be taking our quizzes and tests through Canvas as well. And so if you have some questions about Canvas or uncertain about how to use something in that, just ask me and I can hopefully answer your question. Because that's, especially with the amount of people we have remotely, that's one reason why everything has to go through that. So So for those of you who are remote, you're missing a fun time here in class. We actually have 7 students here, which is great. I think we have 20 in this section this semester, and I think 20 in the later section as well. So what I'd like to do is just highlight a few things on the syllabus. The initial stuff, my office is the same place, ISB 333. Some of this is kind of generic stuff about the class, but what I'd like to skip down to is mostly the grading policy. So in terms of materials, the textbook is the same as last semester. This is just a continuation class, so same textbook. But the grading policy, I just want to remind everyone that in this class, we have 5 exams and 5 quizzes, and you get to drop the low quiz and the low exam, not counting the final. You can't drop the final. And I automatically do that. So I know towards the end of the semester, some people had questions for me about, I want to drop this quiz or this test or whatever. And I just automatically go into the grades and drop the one that's lowest. If for some reason you miss a quiz or you miss an exam and we haven't discussed it beforehand, now if we've had a chance to discuss it beforehand, maybe we can make some other arrangements. But if you just missed the quiz for whatever reason, doesn't matter if you're sick or just overslept or didn't study and didn't want to take it or whatever, that's fine, but that'll count as a 0 and that'll count as your drop. If you miss more than 1 quiz or exam, you only get to drop the 1, so any one after that will be a 0. And then so when you're grading, when I'm doing the grading, it'll be scores and then a 0 if you have that additional missed. So there's a big incentive to come and take all the quizzes, take all the exams so that you can drop that one that maybe you didn't do as well on. And like I said, if you miss more than 1, then you start getting 0s. And that's pretty impactful on your grade. So wanted to just remind everyone of that. The grading scale is there so you can kind of see the grades that you will need to get at the end of the year. So you can kind of keep track as you go along of where you're at. And then a lot of this is boilerplate type stuff about dropping and withdrawing and things like that. One thing I do want to point out is the special services. So if you're a student who has a special consideration, it's not enough to just tell me about it. You need to go through the counseling service that's listed here and get the appropriate paperwork done. And then they'll send me a notice saying what that accommodation needs to be. So it's all confidential, it's all private. But you do have to go through the process in order to get the accommodation. So I do want to remind people of that if you are interested in that. So for this class, well, the larger classes like this one, Gen Chem, we have a lot of students who are choosing to attend remotely. And as you know from last semester, when you take the quizzes and exams, that's typically done remotely as well, or at least you have the option to do that. And so what that means is that the tests obviously are open book, open notes, but what they are not group tests, okay? So the expectation is that you're taking the test or the quiz individually. You can certainly use your notes, you can use your book, things like that. but the idea is not to have people working together on the exams or the quizzes. So if you were to be found to do that, that would be considered cheating, and then there'd be repercussions to that. So I just want to remind everyone of that. The COVID stuff, just as last semester, once again, looks like it's going to be with us this semester. So it does make things inconvenient. We got to wear the masks when we're on campus and in the class. You know, people are going to have COVID issues. In my instrumental analysis class, another class I'm teaching this semester, I've already had some students who've been impacted by that. And so that's just the world we live in right now. And so if you do get impacted by something like that, I would ask that you send me a message to let me know what's going on, okay? People were pretty good about that last semester, keeping me informed on those kind of things. But if that does happen again this semester to someone, hopefully it doesn't, but if it does, please just send me an email or something to let me know what's going on. So I can, you know, because we may have to make some accommodations for you, things like that. The other thing I want to say is, as we're going along the semester, if you're struggling with the class or having some problems, you know, don't struggle in silence. Send me a message. We can set up a time to talk, something like that. You know, the goal for me in the class is to have everyone have a successful completion of the course and to do as well as they possibly can. So if you are struggling with something, I'm more than happy to talk to you about it and discuss what's going on and see if there's something that we can work on to help you out. So if you do have some problems, like I said, don't just sit there and worry about it. Feel free to contact me and we can kind of see what our options are. So what are we doing this semester? So this semester, we're going to start off today talking about liquids and some intermolecular forces. And then we'll kind of go through those. And the goal is we're going to try and do 11 chapters this semester. We did 10 chapters last semester. We'll see if we get through 11 or not. But this is the tentative schedule right now. The schedule is subject to change, kind of depending if we go a little quicker or a little slower. But starting out right now, this week, work on chapter 11. Next week, start on 12. And then not this Thursday, but next Thursday, we'll have our first quiz. So we do have a lot of quizzes. We do have a lot of exams in this class. That is intentional, okay? It's intentional because I'm hoping that by having a quiz and then a test, that quiz, you know, you kind of get you ready, used to taking the exams and get you comfortable with the material a little bit in the beginning. And so then by the time you take the exam on the 2 or 3 chapters, you'll have less to study because you've already studied for a portion of it for that quiz. So kind of the same format as last semester. So as far as I know, we are having spring break. If you remember last semester, they did away with fall break and we kind of compressed things. So as far as I know, we're still having spring break. And so we do have a break in there. That's the stuff in green in mid-March of where we have a week off. Now, I would just say, like most things, that's always subject to change, just depends on what happens with COVID. But I have not heard anything contrary to having that. So hopefully that'll hold up. Okay, so any questions? You can read through the syllabus in more detail yourself when you have some time to do that. But any questions on the bits and pieces that I just kind of went over just now? Okay. So let me pull up the slides then. Okay, can the people on Zoom see my slides? It should say chapter 11.
Yeah, we can.
Thank you. Okay, so as I said, today we're going to start talking about chapter 11, liquids and intermolecular forces. Anyone have an idea of what an intermolecular force would be? What we mean when we say intermolecular?
Inside a molecule.
Okay, inside a molecule. Any other thoughts?
Forces between two molecules.
Okay, we've got between two molecules and within a molecule. So if you think of intermolecular and intramolecular, okay, what do you think the difference is between those two? If I say something's intramolecular, what do we think that would be?
Like within.
Yeah, intra is usually the I guess you call it like a prefix type thing, means within, and inter means in between. Yeah. So if you think about last semester, we talked about intra kind of things. That's the bonding and stuff like that. And so now here, what we're talking about are intermolecular. So we have the forces that are within the molecule. That's the intramolecular forces. And then we have the forces that are between two molecules or more, and that's intermolecular. And it turns out those intermolecular forces are really kind of what determines if things are solids or liquids or gases or things like that. And those intermolecular forces also wind up explaining a lot of what we would call the physical properties of things. So density and boiling point and stuff like that. So that's what we're going to talk about in chapter 11. We're going to talk about what some of that means and try and look at some of the explanations of why things are that way. So in this example, we have two HCl molecules, and we see the hydrogen bonded to the chlorine. That's an intramolecular force. And so that, in this case, is a covalent bond. And we remember what covalent bonds are, right? Anybody remember what a covalent bond is? That's where we're sharing those electrons, right? And so between these molecules, we do have some interaction between the hydrogen and the chlorine. And that's a weaker attraction, but there is an attraction there. And that's that intermolecular attraction that we talked about. So those attractions between the molecules are not as strong as the bonds that hold the compounds together, okay? And you'll hear an example a little bit later that's kind of a contradictory term that they use, and we'll talk about that. But this intermolecular interaction, and here we talk about it could something like melting points, boiling points, viscosity, surface tension, capillary action. So all these kind of like physical properties of molecules. We see that that's impacted by that intermolecular attraction. So the things you want to remember about this is intramolecular. If we talk about that, we're talking about bonds. We're talking about actual chemical bonds, covalent bonds, things like that. And those are pretty strong, right? If we think back, we had to put energy in, a lot of energy in to break those bonds, some more energy than others, but you had to put a lot of energy in typically to break a bond. with the intermolecular forces, and it varies from substance to substance, but you have those attractions as well. And so those aren't anywhere near as strong as the intramolecular, but what those do is those tend to get reflected in these physical properties of the molecules. So it's kind of interesting that you have these competing type of attractions going on. You have the ones that form the molecule, but you also have some of these neighbor interactions type things. So when we think of states of matter, remember we defined the 3 states of matter as gas, liquid, and solid. We see that they have different characteristics, and these characteristics really are, for the most part, a result of those intermolecular interactions. So with gases, remember that gases assume both the volume and shape of the container. So that there we're just saying that if you have a container and you put a gas into it, that gas is going to expand to fill the whole container. It's not going to just stay in part of it. Liquids, on the other hand, those will go to the shape of the container, but if you put 500 mils in a 1,000 mil container, it's not going to fill the whole container like the gas would. It's still only going to fill 500 mils, but it'll go to the shape of the container. And then finally, the solids, doesn't matter what you put them in, they're just going to have their shape and volume that they have. So as we said, we have some expansion with gas, we don't have expansion with liquid, and we don't have anything in terms of movement with the solid. And because of that, gas is compressible. It's pretty hard to compress a liquid, and it's pretty hard to compress a solid. But you think about, we talked also last semester about with gases, that's where pressure comes in, right? You can adjust that pressure, you can compress things and things like that. Gases and liquids flow pretty readily. It says here solids do not flow, and that kind of depends on how you define flow. You can get solids to flow. Think of sugar. You ever pour sugar into something? That's a solid flowing. And then gas diffuses. Diffusion with a liquid is pretty slow, and we'll talk about what that means. And diffusion with a solid, it says it's very slow, but really for practical purposes, it doesn't do anything. Technically, it does move, but not much. So as I said, the difference between those states of matter is that strength of the intermolecular forces. So the stronger those intermolecular forces are, it brings the molecules closer together and has them packed in there more tightly. And so kinetic energy keeps them apart and moving. And so the other thing to remember is that with kinetic energy, that's related to temperature. So you increase the temperature, things move around more, okay? You get that more kinetic energy. So in here, we have a few examples. We have chlorine gas, we have bromine liquid, and we have iodine crystals. And so what you see is in the gas, you don't have real strong intermolecular attraction, intermolecular forces. And so that means these molecules can kind of move around. In the liquid, you're starting to get more attraction, more interaction. And so it kind of slows things down. You can think of it that way. And it brings them closer together. Because remember, we talked about how if things are real far apart, they're not going to interact. It's kind of like you guys are spaced out because of we have the 6-foot distance thing with the COVID, right? We're assuming you're not going to interact. If we packed you closer together, there'd be a greater chance of interaction. With the solids, you have this greater interaction, and so then things get packed in more tightly, And the other things about solids, as we'll see, is the solids tend to have more structure. So in liquid and gas, things are moving all over the place, those molecules. They don't interact much. They're kind of flipping all around the container they're in. Liquids, you have more interaction, but you still have stuff moving around. When you get to the solids, things tend to be packed in there in a particular geometry. And that's one of the things we'll talk about this semester, is some of those geometries. And so there, the molecules are actually packed in pretty tightly, and there's structure to those. There's a whole line of study, and Professor Groneman here is really into this, is crystal structure and studying how crystals are packed in and all that. And that gets down to what we talk about in the solids. So when we talk about the intermolecular forces between these molecules, and in this case, we're going to talk about neutral molecules for right now. There's three types. There's dispersion forces. Sometimes that's called London dispersion forces, sometimes induced dipole interactions. For now, we'll just kind of use the generic dispersion forces to bucket all that. There's dipole forces. Anybody remember what a dipole was from last semester? Dipole, remember, was when you had one of the atoms was electronegative, more electronegative. It would wind up where then that electronegative one would have a partial negative charge to it, and the other atom would have a partial minus, and you get that dipole. So you can have dipole forces, and then finally something called hydrogen bonding, okay? So this is the one I was telling you before. It's a bit of a misnomer because it's not a real bond, okay? Hydrogen bonding is a version of dipole-dipole. We'll get into exactly what that is. But for some reason, a long time ago, they started calling it hydrogen bonding, and that's what everyone calls it. And so, but it's not a bond like a covalent bond or that kind of thing. So don't let that confuse you. But it is called hydrogen bonding. Those first two, so the dispersion forces and dipole-dipole forces, sometimes you'll hear those referred to as van der Waals forces. So once again, to be honest, I think it's more common to just refer to those first two as van der Waals, and then the other is hydrogen bonding. But for our purpose in this class, we will differentiate between dispersion forces and dipole-dipole forces. So the dispersion one is the weakest, then dipole-dipole is a little stronger, and then hydrogen bonding is even stronger. I actually read something the other day that for certain molecules, there have been some studies done, and they suggest that the hydrogen bonding in those molecules actually is a covalent bond. So forget that I said that, but because for this class, we're not going to say it can ever be a covalent, but there have been some instances where that's something that people who study this kind of stuff are still arguing about years later. So when we talk about strength of attractions, and so we have covalent bonds listed first, and then those intermolecular forces. And this kind of highlights just some of the differences between these. And so we see for chemical bonds, lithium fluoride's an ionic bond, and we see the melting and boiling point pretty high. Metallic bonds with beryllium, covalent bonds with carbon. We see how high those melting points and boiling points are. What that tells us is for those bonds, you really got to put a lot of energy in to make something happen. And so that tells us those are pretty strong bonds. When we look at intermolecular forces, so nitrogen gas, we see that's pretty low melting and boiling points. So that tells us those dispersion forces aren't real strong. And then dipole-dipole interactions, in this case for hydrogen chloride, HCl, it's higher. And then finally we get to hydrogen bonding with HF, and that's even higher. But still, these values compared to those, still a pretty big difference. Just reinforces that idea that bonding is stronger than intermolecular forces. So that bonding attraction is stronger than the intermolecular force attraction. It's highlighted at the bottom here with the big capital NOT, hydrogen bonds. Even though we keep saying it's hydrogen bonding, those are not to be confused with the chemical bonds above, the ionic, the metallic, the covalent bonds. Like I said, it's called that, but it's not a true bond. So let's talk about the dispersion forces a little bit. So a nonpolar particle can be temporarily polarized to create a dispersion force. And this tendency of an electron cloud to distort is called its polarizability. So there's things that can happen which will cause not necessarily a dipole forming, because that's a little bit more of a constant permanent thing, but you can do some things to molecules to force a little bit of a shift in the electrons. And that's this polarization, this polarizability here. So what are some of the factors that affect how much polarizability a molecule has, or how much dispersion force is going on? Well, the number of electrons in the atom or molecule. The more electrons you have, the more dispersion force you can have. So it kind of makes sense. We're always talking about these electrons being shared in bonding, or being shared in interactions, or being impacted or moved, kind of shifted around a little bit. So if you have more of them, then you have more opportunity for that. The size of the atom or molecule, or the molecular weight, you can think of it that way. As that goes up, the polarizability increases also. And then the last one we'll mention is the shape of the molecule. So if molecules have similar masses, and remember we talked about isomers before, and isomers were compounds that had the same molecular formula, but had different structures. So that's an example of where they have the exact same molecular weight, but depending upon how they're connected within the molecule, they're going to have a different shape. So it could be a long, say, alkane, straight chain, or it could be something that has branching. And so you've got a little bit more bound up type looking molecule. And so the more compact it is, the less dispersion force. And one way of thinking of that is, when we talk about dispersion forces, we're talking about things interacting, right? If you mush everything together and make it more compact, there's less part of the molecule that's out there to interact with the other molecules. So that's why there that more compact molecule would have less dispersion force. And so here's actually an example. So here on top, we have a linear molecule, N-pentane. The N in front of pentane means it has 5 carbon atoms connected together, and it's in a linear. So N means that it's linear. Down here, we have neopentane, same molecular weight, same molecular formula, but there we don't have the straight chain. We've got branching off some of the carbons. And so it looks almost like a ball there. It's not exactly a ball, but it kind of looks like it a little bit. And what you see there is you see a difference in boiling point. The pentane, N-pentane is 309, and the neopentane is I think that's 282. So what we said is the more compact, the less dispersion force. So if there's less dispersion force, we have a lower boiling point, right? Because those attractions aren't as tight. And so then it doesn't take as much energy to have things change. So does the idea of just the intermolecular forces versus intramolecular and all that, does that make sense so far? Okay. And does it make sense how some of these attractive forces we're seeing impact boiling points and some of these physical properties? Because the physical properties are really talking about how things kind of stick together, so to speak. Okay. So we had that example just a moment ago. And so what we're saying here is the higher the polarizability, the higher the boiling point. And we have some examples here of this. And what that's important because this means if we have higher polarizability, we have more intermolecular force. And we said just a moment ago that the larger the molecular atom, the higher the molecular weight, larger the size, however you want to think of that, more electrons. All those things are kind of saying the same thing, but what that means is when we compare things, the size of the molecular atom matters, number of electrons, things like that. So the more electrons, the bigger the size, stuff like that means you're going to have more polarizability, and the higher the polarizability, the higher the boiling point. And so we just have a few examples here. And you can see differences in these atoms and molecules in terms of boiling point. And it links back to this weight, size, number of electrons, things like that. Let's talk about dipole-dipole interactions. Remember, that was the next kind of interaction, attraction that we mentioned. And so polar molecules, anybody remember what a polar molecule is?
Toward electronegative side of the electronegativity.
Yeah, so polar molecule would be one that you have an imbalance of electronegativity of the atoms. So, and which atoms are the most electronegative? If I look at the periodic table, where on that periodic table are the more electronegative atoms? Top right, yeah. If I'm looking at that periodic table, I look to the upper right, those are the more electronegative atoms. So if I have a fluorine or something like that, then I know I'm going to have, most likely going to have a dipole somewhere. And remember we said dipole means you have, because the definition of dipole is literally two poles. So you kind of have a little bit more of a positive end and a little bit more of a negative end. So we're not saying these are ions, okay? I know that from last semester on some of the exams, I think some people got confused and thought that literally meant they were ions. It doesn't. It just means kind of the electrons are shifted in one direction or another, but not so much that you actually have ions. But you kind of have this more positive end, more negative end. And molecules that have that, we have said we define those as polar molecules. So if we have compounds that have that upper right-hand corner of the periodic table elements in them, then we probably have some dipole interaction going on. And so the presence of a permanent dipole moment, and remember dipole moment means you have this charge, but you also have strength is the way I think of it. So you have the little plus, little minus, but there's also strength component to that. That's why it's called a moment. That this gives rise in polar molecules to dipole-dipole interactions. And what that means is the oppositely charged ends attract each other. We talked a lot about last semester how opposites attract in chemistry, okay? Positive stuff likes to go with negative stuff and vice versa. And so what you see is in this photo here, they're saying that you have dipole-dipole interactions with the red marking there. And then we have repulsions with the blue. And so what that means is the red bonding is matching up a positive and a negative dipole, okay? And so on the blue dots across there, that's showing how you would have a positive and positive dipole. If they're matched up, they're going to repulse. A negative dipole, those are going to repulse. So in the solution, and this is usually talking about solutions when you're talking about these dipole-dipole interactions, not always, but usually it's solutions, is that the molecules are going to orient themselves typically to have that dipole-dipole interaction favorable. And that's that opposites attract thing. But what happens, and this is where it gets more complicated, is when you have bigger molecules, instead of a real small, simple molecule, you've got portions of the molecule that are nonpolar, portions that are polar. So you've got a lot of things going on. It's kind of like a jigsaw puzzle trying to fit it together. And so that impacts things too. The examples we have here, these are pretty simple molecules. You get some of the bigger ones, it gets a little more complicated. So here, to kind of illustrate the dipole-dipole interactions, if we have a series of molecules, and they're all about the same molecular weight. We see 44, 46, 44, 41. So roughly about the same, not big size differences. But yet we see boiling point differences going from 231 Kelvin all the way up to 355 Kelvin. And I always think it's a little deceiving when they put these on Kelvin like that, because like if you look at propane and they tell you the boiling point is 231 Kelvin, well, we all know propane's a gas, right? That's what you have in your barbecue grill if you have a gas grill. So by having it Kelvin, they don't have to put a minus sign. So does anybody remember the conversion for Kelvin? What do you add to C to get Kelvin? Yeah. I think it's 270. Yeah, you're right. No, it's 273, isn't it? Yeah, I think it's 273. So you can see that that boiling point is actually like minus 40-ish C. So when they have about the same mass, same size, the more polar the molecule, the higher the boiling point. Why is that? If it's more polar, why would the boiling point be higher? Anyone on Zoom have a thought on that? Well, let's think about what we said. We said we're talking about dipole-dipole interactions, right? And we said to have a dipole-dipole interaction, you have to have molecules that can form dipoles, right? If a molecule is polar, by definition, it's has a permanent dipole. So we go over here and look at propane. Is propane a polar molecule? No, not at all. That's totally non-polar. There's none of those upper right-hand corner elements there. We look at diethyl ether. We have some polarity there because we have that oxygen. We go to acetaldehyde. Once again, we've got that oxygen there. So that's actually a double bonded oxygen to the carbon there. So it's a little bit different location. So it's a little more polar. But then we get to acetonitrile, and that cyano group, that CN group, that's very polar. And so that's where you see this boiling point going up. Because if it's polar, we're going to have, remember we talked about these interactions? that we can have attractive dipole-dipole interactions, we're going to get that with acetonitrile. For something like propane, we might get some of those weak interactions that we talked about in the beginning, especially if you can do something to the molecule to influence, to kind of mush the electrons around. But acetonitrile, that's the most polar molecule in this series. And so because of that, this is going to have the highest boiling point, because those dipole-dipole interactions, which is what's kind of keeping it together, in order to have it boil, we'd have to break those interactions. Okay, so which has a greater effect, dipole-dipole interactions or dispersion forces? Well, the answer, and we know this because we said this 4 or 5 slides ago, the answer is going to be dipole-dipole interactions. The only exception to that is if you get to a really big difference in size between the two. And so don't ask me what exactly how big it has to be. That's kind of subjective. But just fundamentally, dipole-dipole interactions are going to be stronger than these dispersion forces, unless you have a ton of dispersion forces and just limited dipole-dipole interactions. Okay, hydrogen bonding. So the dispersion forces, this is just my opinion, the dispersion forces are mildly interesting, but in all honesty, they're not that strong, so you usually don't worry about them as much. The dipole-dipole interactions, those are pretty real. Those happen, especially, like I said, in solutions and that. But hydrogen bonding is one that you hear talked about all the time. Hydrogen bonding, especially if you go on and take organic chemistry, you'll hear about hydrogen bonding a lot. And that's because it's for a non-intramolecular bond, it's pretty good, okay? We know those intramolecular bonds, the covalent bond, things like that, we know those are the strongest, but in these dispersion force type stuff, this attraction type stuff between molecules, hydrogen bonding is a pretty big deal. And so it's an offshoot of the dipole-dipole interactions in reality, except there's kind of like a strict definition about it, is if the dipole-dipole interactions are experienced when hydrogen is bonded to either nitrogen, oxygen, or fluorine, this is pretty strong. And these are the interactions we call hydrogen bonds. And so here, over on the right, we have some examples of hydrogen bonding and covalent bonding. So here we have the first one, we have 2 water molecules. So we have hydrogen bonded to oxygen. We have 2 of those hydrogens bonded to an oxygen. Those are covalent bonds. But because the hydrogen is bonded to an oxygen, we know we're going to have a dipole there, right? The negative is going to be over on the oxygen, and the positive will be over towards the hydrogen. And so in this second molecule of water, the same thing's going to happen. That those oxygen there is going to have that slightly negative, and then the hydrogen will be slightly positive because those electrons are kind of mushing over towards the hydrogen, rather the oxygen. And so what that means is now we've got a hydrogen that would like to have a little bit more electron involvement, and we've got oxygen with extra. And so that's where we get a dipole-dipole type interaction there between the molecules, okay? And so this interaction, this hydrogen to an oxygen, there in this case, that's called a hydrogen bond. So as you may have guessed, hydrogen bonding always involves hydrogen, okay? That's why it's called hydrogen bonding. So If it doesn't have hydrogen involved, it's not hydrogen bonding, it's something else. That hydrogen that's involved has to be bonded to either oxygen, nitrogen, fluorine, one of those. What do those three elements have in common, nitrogen, oxygen, and fluorine? Well, they're in that upper right corner of the periodic table. That's that electronegative area. And so they want those electrons. They want to pull those electrons away from the hydrogen. Okay, and that's what creates that ability then to have this stronger intermolecular bonding, which we're calling a hydrogen bond, and is a little bit stronger than a regular dipole-dipole interaction. Okay? Any questions about this? This is a big deal. It may not seem like it now, but like I said, if you go on and take organic in particular, but even a lot of things in chemistry, hydrogen bonding is used to explain a lot of things. I know you had said you'd had organics and are taking it. So have they talked about it much in your class yet?
In organic one, they did.
They did, yeah. So, you know, it's funny as you teach Gen Chem, some of the stuff we go over, I have to be honest with you, I think, yeah, they'll probably never see this again. Other things, it's like, if people go on in chemistry, they'll see it a lot. This is one of the ones you'll see a lot. So make sure you're comfortable with kind of the definition of hydrogen bonding and what that means and why it's important. Okay, so this is just kind of a repeat of kind of what we were saying, but I'm going to go over it again just because I think it is important. So that hydrogen bonding arises because of that high electronegativity of nitrogen, oxygen, and fluorine. And so in these simple examples here, they show what we talked about. Remember, the plus part of this represents that partial positive charge. The arrow points to the negative part. And so what that's telling us then is that, you know, hydrogen just has the one proton. There's no inner electrons, anything like that. And so that's one reason why this is easy to kind of get this to occur, to get this dipole to form. But this is important, and this is what this explains, as I said before, why you get that occurrence. That hydrogen bonding needs this electronegative atom, nitrogen, oxygen, fluorine, next to that hydrogen to kind of do that electron shift. Then that leaves you with this electron deficient hydrogen, and then it's looking to other molecules that have something that can give it, to share some of that through the intermolecular forces. Okay. So it's, you know, it's cold out these days, and it's not uncommon to be driving along. If you see some water, there's some ice, and the ice is always floating. Does anyone ever wonder about that? Because if I take a rock and throw it in that water, assuming there's no ice on top, what does it do? It sinks. It goes to the bottom. So usually, at least for myself, when I think of solids, I think of stuff that is heavier than a liquid. I always think of solids heavier than a liquid. So if I have a solid and I put it in a liquid, I expect it to drop. It doesn't always. Sometimes the stuff floats in that. But in this case, it's water. In water, you're not changing the structure. It's not like it's a different compound or something. But yet, ice floats. It floats because it's less dense. So I always find that interesting. I find that interesting that solid ice is less dense than liquid ice. And then the other interesting thing is it takes up more space. It's less dense, so it floats, and it takes up more space. And an example of that is, and this is a pretty good one, where they have water in a, looks like an old soda bottle, then they froze it, and you'll see that where if you ever do that and you fill it up too much, it'll crack the bottle sometimes, or it'll come out if you don't have a lid on or something like that. So what this is doing, excuse me, this is an example of hydrogen bonding at work. And so hydrogen bonding makes the water molecules farther apart in the ice, in the frozen, than in the liquid. And so here that we actually have some bond distances. So the covalent bond is about 1 angstrom. This hydrogen bond, the intermolecular force is about 1.8 angstroms. But that's the reason why ice floats, why it expands, water expands when you freeze it, things like that. It goes back to this hydrogen bonding that's going on in water. Hydrogen bonding is a big deal with water. And if you think about it, water is often a solvent in reactions and things like that, or just in a lot of things we do. And so that hydrogen bonding plays a pretty big role in a lot of that stuff. Okay. There's something called ion dipole interactions. And these occur when you have an ion, so an actual ion, and then a polar molecule. So in this case, we have chloride ions. In this case, we have sodium ions. And what you see is, and the molecule that they're showing is water. And so what you see is, we think about that dipole that forms in water. So the little white balls here are the hydrogen atoms. The red one is the oxygen. And so we know that we'll have that partial positive charge on the hydrogens. We'll have that partial negative charge on the oxygen. And so when these ions are put into solution, you're going to have, in this case, the chlorine, which is negatively charged, associating with the water molecules, but the water molecules are going to orient so that that partial positive charge is what it's facing towards. That's the intermolecular force that's going to occur. Just the opposite on the bottom for the sodium atom, that's the positively charged atom. And so here we see the water molecules orient a little differently so that the red ball, that oxygen, which has that partial negative face to it, is going to interact with the sodium. So the cations are attracted to the negative end of the dipole. The anions are attracted to the positive end of the dipole. The strength of these forces is what makes it possible to dissolve ionic substances in polar solvents. And the biggest polar solvent you'll see is water. So if you think about it, when you think about salts in general, the most common salt people think of is table salt, okay? That readily dissolves in water. But salts, remember our definition of salts is where you have that positively charged cation, negatively charged anion, and it gets down to the bonding of it and all that fun stuff. Salts in general dissolve in water. And this is why. It's because of the orientation of these dipoles in water and its ability to interact with the positive and negative. So what you probably are realizing is that we talked about chloride up here, we talked about sodium down here, but you don't have just chloride ions. You don't just have sodium ions. Most likely this was table salt, sodium chloride, right? And you put it in there and one solvent, in this case water, because of that dipole that it has, it can interact and have forces with the cation and the anion both. And that contributes to that ability to solubilize things, is to be able to interact with them both. Okay, let's talk a little bit about types of intermolecular forces and kind of what that means. So if we look at the first, over here on the left, we have the intermolecular interaction. So we have dispersion forces, we have dipole-dipole, hydrogen bonding, and then ion dipole. So we see for dispersion forces, where there's atoms, nonpolar, polar molecules that can form hydrogen bonding, or ionic solids dissolved in polar liquids. Dispersion forces factor into all of that. And that's why I was saying earlier, you know, the dispersion forces are just kind of there all the time, and sometimes they make a difference, sometimes they don't. Dipole-dipole interactions, we see to be able to have dipole-dipole interaction that has to be a polar molecule. So that leaves us with one of these choices. And the only difference there is that the ones that can do hydrogen bonding, we give it that special name of hydrogen bonding. And that's where you've got these oxygen, nitrogen, fluorine atoms involved somehow. So, but we see for dipole-dipole, things have to be polar. Okay, and that makes sense. And then the next one, hydrogen bonding, we said it's this special type of dipole interactions. And then finally, the last one, ion dipole interactions. Well, for that to happen, you have to have ionic solids. Okay, so you have to have salt. The strongest force on here really dictates what's going to go on between the molecules. So if you've got something that can hydrogen bond, these dispersion forces aren't that important. If you've got something that can do just any type of dipole-dipole interaction, once again, the dispersion forces aren't as important. Same with these ionic solids dissolved in something like water. So, like I said, the dispersion forces are there, but if you have any of these other things, that's going to override it. So just some general rules about these intermolecular forces. So when two molecules have similar masses and the shapes have similar masses and shapes. So in other words, one isn't like a long linear type molecule and the other one is a bunched up molecule. So they have similar mass, similar shape, then the dispersion forces are going to be pretty similar. When two molecules have very different molar masses and there's no hydrogen bonding, the dispersion force determines the substance with the stronger attractions. And that's what we said before, is that if you've got some polarity associated with it, that's gonna override it. But if it doesn't, then dispersion force takes over. Okay, any questions on the stuff that we've talked about so far? Okay, what I'd like to do is, so here are some homework problems you can work on. What I'd like to do though right now is take a look at a couple of these just to make sure everyone is comfortable with them. So let's look at 1117. So in 1117, they ask us to describe the intermolecular forces that must be overcome to convert these substances from a liquid to a gas. And the first one is SO2, so sulfur dioxide. So when we look at that molecule, what we want to look at is we want to look at, first thing is to decide, is this polar or not? Because remember, we talked about hydrogen bonding and dipoles and all that being a big deal in this. And SO2 is polar. Okay, you have different electronegativities of the oxygen and the sulfur. And so this is a polar covalent molecule. So does it have any hydrogen bonds? Is it hydrogen bonding? Why not?
It does have a hydrogen.
Very good, yeah. There's no hydrogen there. So we've got polar dipole-dipole interactions because it's polar, but we don't have hydrogen bonding because there's no hydrogen. And so what that tells us is we got to overcome that dipole-dipole interaction. We also have to do the dispersion forces, but as we talked about, in terms of ranking them, we're more concerned about that dipole-dipole interaction. The next one, CH3COOH. How about that? Is that polar? Any thoughts on whether that's polar or not? It's polar, we got those oxygens. When you got the oxygens floating around, that kind of should send off the alarm that you're probably gonna have a polar molecule. How about hydrogen bonding? Do we have any hydrogen bonding? Why is that? Yeah, why are you saying you have hydrogen bonding? Yeah, the hydrogen, when you write something like this means the carbon has a double bonded oxygen to it and then a single bonded OH to it, is what that means. The key is not so much the double bonded oxygen for what we're talking about, is that OH tells us that the hydrogen is bonded to the oxygen. And remember, that was one of our definitions of a hydrogen bonding situation. So it's a polar covalent molecule. We've got a lot going on. We've got the dispersion forces, we've got dipole-dipole, but the big one is we've got the hydrogen bonding interactions. Because we said that's the one on our little table, that's the one that's going to dominate. The last one, hydrogen H2S, hydrogen sulfide. That's polar as well. There's no hydrogen bonding there because even though we have hydrogen, it's not bonded to either an oxygen or nitrogen or one of those, or fluorine. Okay, any questions about this one? Okay, let's look at 1119. So in 1119, it gives us a series of molecules and wants us to list them in order of increasing polarizability. Okay, so we start at methane and go up to whatever GeBr4 is. And what we know is that polarizability increases with molecular weight. And so these numbers that I have written under each of the molecules are the molecular weights. So that tells us that polarizability is increasing as we go up to high molecular weights. What was one of the reasons why we said that the higher size, the higher molecular weight makes a difference? What was one of the things that comes along with that? You just have more electrons, right? And so you have more electrons, you have more opportunity to have that polarizability. Then in part B of this, predict the order of boiling points. Well, if you have higher dispersion forces, then the boiling point goes up, right? Because if there's more dispersion forces, that means those intermolecular forces are a little stronger. If those are stronger, the boiling point goes up. So the order for boiling point will be the same as that polarizability. So once again, that size in this case and that polarizability correspond together. Okay. Let's look at 1125. So in 1125, what atoms must a molecule contain to participate in hydrogen bonding with other molecules of the same kind? So what did we say we need for hydrogen bonding again? I forgot.
Hydrogen.
We need hydrogen, and what else do we need? We need hydrogen. But we also need one of these three, right? Fluorine, oxygen, or nitrogen. So we need the hydrogen, but do we need something that's real electronegative to kind of have that electron shift going on? So if we look at these examples, we're going to try and decide which ones can form hydrogen bonding. So CH3F, I have there no hydrogen bonding. Did I make a mistake there? Because we've got hydrogen and we've got fluorine.
The shape,
It's a shape,
like the fluorine doesn't have a bond with hydrogen, it bonds with
right? That's exactly right. So she said that the fluorine isn't bonded to the hydrogen, it's bonded to the carbon. And so if it's not bonded to that electronegative atom, you don't get that dipole. So that's why that one. Now the next one, CH3NH3, or NH2, I think that is. Can't read my own handwriting. Hydrogen bonding there. Why is that one good?
Because you got NH2, you got N, H.
Yep, that's right. You've got NH, you've got the hydrogen bonded to the nitrogen. So you got a hydrogen atom, you got that electronegative nitrogen, and you've got them bonded together. So that means for that molecule, that's going to have some hydrogen bonding involved. The next one, CH3OH, methanol. Hydrogen bonding there? Yep, because hydrogen is bonded to an oxygen, right? And so we can have that electronegativity impact, and we've got the hydrogen atom. And then finally, CH3Br, that looks suspiciously like the first one. Okay, so that same logic there of the hydrogen is bonded to the carbon, and so it's not bonded to anything electronegative. All right. Okay, so we've been talking a lot about boiling point so far, but these intermolecular forces impact some of these other physical properties, and here's some examples of them. So the boiling point, as we've been talking about, but it also impacts melting point, okay? It also impacts viscosity. Does anyone know what viscosity is? So if I say something is real viscous, what do you think when I say that? Is syrup viscous? Yeah. Is water viscous? No. So you would say syrup has higher viscosity than water. A real simple way to remember viscosity is how hard is it to pour it out of a container? Okay, if it pours really slow, like syrup is usually kind of slow, it's probably pretty viscous. Surface tension is another physical property. So capillary action, another one. And we'll talk about surface tension and we'll talk about capillary action a little bit. But for today, we're going to wrap up for today. Any questions about what we went over today? Okay, all right. Well, we'll continue on with this on Thursday, and thanks for being here.